So in this video, we're going to look at an example. In a January 2020 poll conducted by Zogby Analytics, 565 of 1,028 randomly selected adult Americans reported being registered organ and tissue donors. So we have 5 parts. In Part A, we want to obtain a point estimate for the population proportion P of adult Americans who are registered organ and tissue donors. B, we want to verify that the requirements for constructing a confidence interval for P are satisfied. C, we want to construct a 95% confidence interval for the proportion of adult Americans who are registered organ and tissue donors. D, we want to interpret the interval. And E, is it possible that the proportion of adult Americans who are registered organ and tissue donors is higher than 60%? Is it likely? So we're going to look at each one of these on a separate sheet. I'm going to begin by writing down what we learned in the problem statement. So there was a sample of 1,028 adult Americans, and of those 1,028 adult Americans, 565 stated that they were registered organ and tissue donors. So in Part A, we're supposed to find a point estimate for the population proportion of adult Americans who are registered organ and tissue donors. In other words, what's the true proportion of adult Americans who are registered to donate organs and tissues? Well, our point estimate is going to be P hat. And we're going to find P hat by taking the number of successes, the number of individuals with the given characteristic, divided by the sample size. So that is going to be 565 divided by 1,028. So if I bring in my calculator, 565 divided by 1,028 is 0.5496. So this is approximately 0.5496. So about 55%. So based on this sample, we would estimate that about 55% of adult Americans are registered organ and tissue donors. But we want to find a confidence interval for the true proportion, and that's what we're asked to do in Part C. But before we can do that, we need to make sure that we're able to do that. So, question B, if I bring that back in, we're supposed to verify that the requirements for constructing a confidence interval for the population proportion are satisfied. So we have 2 conditions. We need to make sure that N times P times 1 minus P is 10 or bigger. Now, this is what we really want, but we don't know P, so we're going to have to use P hat in its place. We also need to make sure that our sample size is less than or equal to 5% of the population. So we got to check these 2 conditions. So in this case, our sample size was 1,028, and P hat was 0.5496, and so 1 minus 0.5496 we're going to find as well. So if I bring my calculator back in, 1,028 times 0.5496 times 1 minus 0.5496, that is 254.47 approximately. Now that's certainly way over 10, so we meet that first condition. N times P hat times 1 minus P hat is 10 or bigger. Now the second condition, we need to make sure that our sample size is less than 5% of the population. The only trouble is we don't really know exactly what the size of the population is. So our 1,028 has to be less than or equal to 5% of the population. Again, we don't really know what the population size is, but we can kind of think about that. So our population is adult Americans. So how many adult Americans are there? Well, we don't know exactly, at least I don't know exactly, but I do know that altogether there's over 300 million Americans, and at least a third of those I would think would be considered to be adults, so that would be 100 million. So the population size here has to at least be 100 million, and 1,028 is certainly less than 5% of that. To put a little more firmness on this, if 1,028 is less than or equal to 0.05 times the size of the population, well, if I just do a little algebra here and divide both sides by 0.05, 1,028 divided by 0.05 is 20,560. So 20,560 is less than or equal to n. In other words, n is greater than 20,560. So as long as our population is larger than 20,560, then our sample size is less than 5% of the population. Well, certainly the number of adult Americans is greater than 20,560. So certainly we meet that condition, even though we don't know precisely what the population size is. Clearly we meet that. Now, part C, I want to look at on a clean sheet just to make sure I have plenty of room. So as always, we're going to be able to do these problems using technology, but I want to start by looking at it by hand so that you have an appreciation of what's really going on here. And then once we have a grip on that, then we'll use the technology as a general rule to do these. So in part C, we want to construct a 95% confidence interval. And so we already know our point estimate from part A. We know that p hat is equal to 0.5496. So in order to finish my confidence interval, I need to calculate the margin of error. So we need to calculate E. Well, we've learned that our formula for E is z sub alpha over 2 times the square root of p hat times 1 minus p hat divided by n. So I know p hat and I know n, but I don't know what this z sub alpha over 2 is, and so we need to discuss that. I'm going to go ahead and write down so that I don't have to look it up later. N was 1,028. So I need to figure out what this z value is that's going to be connected to this 95% level of confidence. So I'm thinking about a normal distribution, specifically a standard normal distribution. So 0 is here in the center. And I need to find the z values so that this area here in the middle is 95%. So that area needs to be 0.95, which means the area in the two tails makes up the other 5%. Now, because of symmetry, half of that 5% is going to go in each tail. So this area right here is going to be 0.05 divided by 2, which is 0.025. And this area in this tail here is also 0.05 divided by 2, which is also 0.025. So I need to find the z-scores that are separating this middle 95% of area from the outer 5%. Now again, we've learned ways to do this previously back in earlier chapters. So we can do this by hand, we can do this with technology. So I'm going to begin by reviewing how we do this by hand. By hand, we can use our normal tables. So here I brought in my normal table, and I'm looking for the area over here in this left tail to be 0.025. So I'm going to think of that as 0.0250. So if I look through my table, right here is 0.0250, and that corresponds to a z-score of negative 1.96. So this value right here is negative 1.96, and by symmetry that means this one is positive 1.96. This is my z sub alpha over 2, so the z-score that corresponds to a 95% confidence interval is 1.96. We call that a critical value. So that is our critical value. Now I also want to point out real quick, on your standard normal table, at the bottom of the second page of that table, we have the most common critical values that we're going to use. So for example, if you look here in section B of this table, right here it has a 95% level of confidence, and it tells us that critical value is 1.96. If we had a 90% level of confidence, then it would be 1.645. 98 and 99, we can see 2.33, 2.575. So we can look those values up using the table. We could also, if you'll remember, use the inverse norm command on our calculator, or we could use the normal calculator in StatCrunch to figure that value out as well. Just quickly, if I bring in my calculator, if I go to inverse norm, which is the second distribution button in number 3, inverse norm, so if I make, say, 0.95 the area in the center, as I have it marked here, then I get those two critical values, negative 1.96 and positive 1.96. Now, if you have an older calculator, remember you always have to use the area to the left, so we would enter, say, 0.025, and that would be the left area, and so we would get the negative 1.96, and by symmetry, then the other value has to be positive 1.96. So we could use the calculator to find that. We could also use the normal calculator in StatCrunch. So let me review that with you really quickly. So in StatCrunch, if we go to Stat and Calculators, and then we go to Normal, then if I'm using the left tail, let's say, so I'm going to use less than, and so I want that area to be 0.025 in the left tail, so I enter 0.025 in this outer box and say compute, and that gives me the z-score, negative 1.96 if I round here. So this value here is negative 1.96. I could do the same if I change this to greater than. Then if I want this area in the right tail to be 0.025, then I compute, and so that gives me 1.96. And I could also do between, so if I want the area in the middle to be 0.95, then I could compute, and it'll give me both the negative 1.96 and the positive 1.96. So this is how I could use StatCrunch in order to figure out what those critical values are. So we have options. We can do it by hand, we can use the calculator, we can use StatCrunch. We could use other types of technology as well. We just normally use the calculator or StatCrunch in our class. Okay, anyway, once we have that value found, we have the critical value, then my margin of error is going to equal that critical value, 1.96, so that's my z sub alpha over 2, times the square root of p hat, which is 0.5496, times 1 minus that, so 1 minus 0.5496, close my parenthesis, and that's over n, which is 1028. So I need to do this calculation, and that will be my margin of error. So if I bring my calculator back in, 1.96 times the square root of 0.5496 times 1 minus 0.5496, close the parenthesis, divided by 1028. So that gives me 0.0304 if I round to 4 places. So this is approximately 0.0304 for our margin of error. So if I take my point estimate minus the margin of error and the point estimate plus the margin of error, that's going to give me my confidence interval, and we're going to usually put that in interval notation. So if I take 0.5496 minus 0.0304 and 0.5496 plus 0.0304, that's going to be my confidence interval. So 0.5496 minus 0.0304, that is 0.5192, and 0.5496 plus 0.0304, that is 0.5800 if we carry out to 4 places. So my confidence interval is 0.5192 to 0.5800. So that's part C. I'm 95% confident that the true parameter is going to be within that interval. So question D. Question D, we're supposed to interpret the interval. So I actually already said that. So we are 95% confident that the true proportion of adult Americans who are registered organ and tissue donors is between 0.5192 and 0.5800. So again, between about 52% and 58%. We're 95% confident that somewhere between 52% and 58% of adult Americans are registered organ donors. Question E. Is it possible that the proportion of adult Americans who are registered organ and tissue donors is higher than 60%? Is it likely? Well, we're 95% confident that the true proportion's somewhere between 51.92 and 58%. Is it possible that the true proportion is 60%? That's possible, but that's outside of our confidence interval. So, is it possible? Yes, it's possible. But that would be a really unusual result. So, is it likely? It's not likely. So it's possible that the true proportion's outside of our interval, but it's not likely. That would be an unusual result. Let's take a look at another example in another video.